So look around.
All right, so let's get started. Okay, so today we have Sean Lindsay, who most of you know because he is a member of our faculty here. So Sean is our astronomy coordinator. He has basically, as I understand it, revolutionized our undergraduate astronomy education. But before that, he was a postdoc at Oxford. And before that, he was a postdoc at UT. You were at New Mexico State University as a graduate student, and before that, you were at UT for undergrad, right? Did I get the whole thing? And so that's the reverse chronological version. But anyway, now he is here with us, and he's going to talk to us about his work studying the dust of Comet Hale-Bopp.
Hale-Bopp.
Hale-Bopp. Okay.
Not the
great.
special how you say that one.
Okay, go for it.
All right. Well, thank you, Tova, for inviting me here. As some of you probably heard of before this started, I haven't given a research talk in quite a while. So I'm excited to do this, and I will apologize before I get started. I did not have time to make this a short talk. So I'm going to start a timer right now, where in 39 minutes, I know to start wrapping things up. And that should leave plenty of time for questions, because questions are important. So let's see, make sure everything is changing. Instead of actually spending a whole lot of time going through, like I'm going to do an introduction, methods, results, discussion, summary, all that, we're going to hit all that as we go on through. So I'm not going to take a whole lot of time with this one right here. What I want to do is go ahead and jump right in. And I want to talk to you about the big picture. Because anytime I do any research project, I always like to keep the biggest picture in mind. Sort of like makes it exciting to remember what it is that I'm working on. And for me, I work on the formation of the solar system. So all of my research, including the research I'm presenting today, deals with how do we go from a giant molecular cloud. So I have one picture here on the screen over on the left. How do we go from a giant molecular cloud to the entire diversity that we see in the solar system, where we have the sun, we have all the planets, and we have all the small things, all the small bodies, our comets and asteroids. Today's talk will be about comets. And then things like dust particles, CP-IDP stands for chondritic porous interplanetary dust particles. We like our acronyms just like the rest of the physics world. And these are thought to be comet dust particles. And then things like meteorites. So how do we go from a giant nebula that spans light years across, collapse that down to form the diversity of our solar system? And what kind of interesting questions can we ask about each one of these objects that can give us insight into how our solar system formed? So we should do a quick review. I'm not quite sure where everybody's background is on the formation of the solar system. So I'm going to do the quick dirty review on how our solar system formed. So typically we'll call this the nebular condensation theory. And then I'm going to throw in some modification as well, where we start as a giant molecular cloud. This one is just a cartoon graphic, not as nice as the previous picture. And then within this molecular cloud, these dense cores, regions that are cold and dense, they get perturbed, they get squeezed a little bit, and all of a sudden gravity starts to win and they start to collapse underneath gravity. Conservation of angular momentum will make them spin faster and faster. And as they spin, oh, no problem. So as they spin in strength, they'll spin faster and faster and faster, and they'll flatten themselves out into a disk of gas and dust, the so-called solar nebula. And it's out of this solar nebula that we are able to form the planets and all the small leftover bits, our comets and our asteroids. And then a whole bunch of fun gravity interactions happen that clean up the solar system and somehow will leave us with our current solar system. So I like to break this down into different formation eras. There are a number of ways that you can break out the stages of formation. I'm going to break it down into the eras where we have the molecular cloud and collapse to our solar nebular disk. So down to our solar nebular disk that's up in the top right, to the grain formation era, because we have to get the solid bits that we're going to build all the planets out of, that we're going to build comets and asteroids out of. So we'll call that the grain formation or the pre-accretionary era, before the planets start getting constructed, before we make our planetesimals and protoplanets. Then we have our planet building era, where we're building things like here's a picture of a comet, and we're building like the proto-Earth, proto-Jupiter, proto-Saturn, and the Kuiper Belt objects, all the fun things in the solar system. And then we have the modification era. This is really, really, really exciting and a very active area of research right now, where you'll have gravitational interactions and you'll have Jupiter moving its way through the solar system, as physics would predict that it does, which sort of mixes up everything and cleans up our solar system, sort of rearranges where everything is just a little bit. So modification era. Then that ends. Now we're about 3 billion years ago. And it's just evolution to present. Small things are still going on. We're technically still kind of forming. We're still cleaning up. We still have leftovers. And over here on the right, what I'm going to be focusing on today is the grain formation era. And I'm going to be using comets, specifically Comet Hale-Bopp, to see if we can figure out what's going on in this grain formation era. Where are grains coming from? How are they forming? And what are they like? And what kind of information can they give us about the grain formation era of our solar system formation? So just a little bit more. So the previous one where you just collapsed down into the solar nebula, disk made out of gas and dust, and gravity, yes, it still works. Thank you for the test. You can never stop testing things in science, right?
Yeah.
So the collapse down to the solar nebula is sort of the nebular part of the nebular condensation. The other part of this is the condensation part. And I'm only going to do the broad brush details on this. If you want more details on this later, please ask questions. But we essentially have our solar nebular disk. We have the sun forming in the center. And then you'll have a disk. The midplane is the hottest. And within the midplane of the disk, as you move further and further away from the sun, the temperature drops. It gets colder and colder and colder. The midplane has sufficient densities and sufficient temperatures, for as you move out, the temperature will drop and you can condense out of a vapor different solid materials. So the innermost regions where it's super hot, you can get oxides and metals. Then you're going to get our silicates. This is where I'm going to be focusing on. And they have a condensation temperature of about 1200 Kelvin or so. So we're going to need regions of the disk if we're going to be looking at silicates that form in the solar system. We're going to be tracking where, or regions of our solar nebula where the temperature was sufficient to condense out silicates. And the rest of these, I'm not going to bother going through all of those, but you can see we have this nice condensation sequence. And it's just telling you what will form at what temperature, which you can map to distance away along the midplane of the disk. So this is how we get all of our solids that will eventually build the planets out of. So this is the condensation sort of theory part. And I'm going to be focusing on our silicates. And down here on the right, I have an image. This is, so it's cut off, hopefully not on Zoom. Down here, this is from Kobataki et al. 2008, where they did vapor to solid condensation experiments of making forceroid grains. Scale bar is about 2 microns right here. So you can see you're forming very, very solid crystalline grains. And one thing I want you to keep in mind is that this is a very nice geometric shape. The shape of our crystalline silicates, especially forced right, is going to be a big part of this talk. And it's a big part of what I'm driving at, is trying to understand how the shape of this might affect the spectrum of Hale-Bopp. So I do need to go through a little bit of Silicates 101. We're a physics department, not a geology department. And I'm going to be talking about both olivine and pyroxene. This one is particularly orthoperoxene. There's a clinopyroxene as well, but I'll just refer to orthoperoxene just as pyroxene for the rest of this talk for simplicity and not get anybody too confused about what's going on. But these two silicates are the most abundant silicates in the solar system, the most abundant silicates on Earth. And they have their solid state solutions right here, their chemical formulas, where you can have magnesium or iron. Those are the 2 primary metals. And notice this is going to be the same for both olivine and for pyroxene. And then you have some silicon and oxygen as well. And you can vary how much iron versus how much magnesium you have. And that can be used, this is leveraged by a lot of people as well, on formation conditions. Whenever you have low oxygen available in your reducing environment, you'll tend to form magnesium-rich silicates. Where if you add a little bit of oxygen, then you'll tend to form iron bonds. So if you want to look over on this part of the screen, so over the right-hand side for the Zoom people, I have just a picture of what the actual crystalline silicate looks like. And we're looking down at the unit cell where you can actually see where the different atoms are, the oxygen, silicons. And then in the center of all these, you have either magnesium or iron. And these things are going to be moving around in there. And this entire unit cell can rattle around with bending and vibrations. And it's going to give us all sorts of interesting spectral features. And then there's no geologist this time. I'm okay. I could just say amorphous silicates and nobody would want to like run up here and punch me or slap me. So amorphous silicates is a term that we use in sort of cosmochemistry. Amorphous silicates don't really exist. You just call them glasses instead, but amorphous silicates to us are ones that were once crystalline and have had their long-range crystalline order disturbed, usually by cosmic rays or collisional processing. So we'll have amorphous silicates, and then we have our crystalline silicates. So there's my Silicates 101. Now let's go ahead and start taking a look at these silicates in comets. I'm going to be focusing on Hale-Bopp. So I have this beautiful picture of Hale-Bopp over here at Great Star Skies in 97 and 98. Hopefully some of you were able to see it. It was one of the first comets that I ever saw and remember seeing. And it was bright enough where you could see it in broad daylight. And my dad took me up the Foothills Parkway night after night after night. We brought some telescopes up there and we observed Comet Hale-Bopp. And I like to think that maybe that influenced me to write my dissertation about Hale-Bopp. It definitely influenced me to be interested in space and astronomy. But one thing to keep in mind is comets formed cold. Comets are cold objects. And just a roundabout number, less than 50 Kelvin or so. How do we know that? Well, we can see what kind of ices are in comets still. Whenever they become active, we can see what ices are there. The ices are there, things like nitrogen ice or carbon monoxide ice, are super cold ices. So if that comet was ever warmer, we would have lost those ices. So by the fact that we still have those ices, comets are formed cold and have remained cold for 4.6 billion years. They are the freezers of our solar system. So any of the silicates that we see in there is telling us something about the grains that got incorporated and formed into comets. So we're going for the grain formation era before we collected them to form the comets. And what's really interesting is by examining active comets, ones that have developed a coma and tails, they've gotten close enough to the sun where they're sublimating their ices into gases and picking up some dust. We can look in the mid-infrared from about 6 to about 45 microns. So this is kind of light that we're all giving off right now. So thermal infrared light, we can look there and we see silicate features in emission. So this dust is warm and therefore glowing. This allows us to tell that there are silicates in the comets, and we can even get broad brush strokes of what kind of silicates they are. There's a lot of modeling stuff. I have some supplemental slides on that if you really want to get into the specifics of it, but we can see that there are silicates in emission. And then there's Comet Hale-Bopp. And the observations I'm going to be using for the remainder of this talk, whenever I talk about Hale-Bopp, this observation right here, this is made with the Infrared Space Observatory, the telescope that happened before Spitzer, the first infrared space telescope that we had that could do spectroscopy. And there are no current space telescopes that can do infrared, mid-infrared spectroscopy. So we're a little bit sad at the moment. You'll see that a lot of my references are dated because of that. We don't have any good data anymore. But this is a spectrum of Hale-Bopp from the ISO, the Infrared Space Observatory. Down here we have wavelength. It's going from about 8 microns to about 40 microns. And we have a spectral energy distribution. So this is lambda, F lambda. You can just think about it of how bright each wavelength is, the flux at each wavelength. And in this spectrum, you can see all of these peaks right here, these narrow peaks. These are from a crystalline silicate, crystalline olivine. And then you can see this broad feature here around 10 microns and this broad feature centered around 17 microns. Those are from our amorphous silicates. And if I want to try to draw a black body through here, you kind of touch this little trough that's about at 15 microns or so. So these features are in emission. Previous analyses of this spectrum put that we have a crystalline fraction. So this would be the mass of crystalline silicates divided by the total mass of crystalline silicates plus amorphous silicates. So basically a percentage of how many crystalline silicates there are. They range from about 0.4 to 0.75. It changes a little bit as the comet becomes more active, and it changes based on what model you're using. Another important thing to keep in mind. And if you're in Zoom land, you can see that I have the crystalline fraction F-crist equation at the bottom. And now I want to go ahead and show you what the spectral features that we're going to be looking at and what I'm going to be trying to model are. In fact, these are from some of my models, but it's also a good tool to demonstrate what's going on. So along the x-axis, we again have wavelength in microns going from about 8 to about 40 microns. And then I have plotted here the spectral energy distributions, lambda F lambda, of just different components. It's showing us what the silicate features look like. Now you can see the silicate features for amorphous silicates are these broad ones. This sort of yellow line is for amorphous peroxine. The green line's for amorphous olivine. And you get the broad features, one feature centered at about 10 microns, another one centered near 17 microns or so, peaking there. And then we have crystalline silicates, and the two I'm going to talk about are the magnesium end member of olivine, forsterite, so very magnesium rich. 90% of all of the cations are magnesium, so that leaves very little iron. And then the iron end or the magnesium end member for peroxine is enstatite, and that one is in orange. You can see they have very narrow band features due to crystalline resonances. And here you can see the enstatite ones, and all of these are going to be components that we're going to try to extract out of our spectrum of Hale-Bopp. And I want to go ahead and make sure everybody has a good picture. So I made a really big plot of the spectrum of Hale-Bopp. This is the ISO data, and then we've added in a little bit of HiFogs data to beef out this 10 micron feature over here. And I've put little green bars showing where the forsterite features are, that magnesium end member of iron. So you can see that we have features for our crystalline silicates at 10, 10.5, 11.2, 16, 19, 23.5, 27.5, and 33.5. You get some more features longer, but this is where I'm focusing because this is the ISO spectrum that we have. So now you can see that Hale-Bopp definitely has silicates. You can see the broad amorphous features, and now you can see these narrow crystalline peaks. So what is this really telling us? Well, this is telling us that there are crystalline silicates in Comet Hale-Bopp. This is going to be important because if we just go and start looking around, just take random lines of sight through the interstellar medium, the stuff that's between the stars, so looking at molecular clouds and other collections of gas and dust out there, and actually look at the crystalline fraction of just dust that's out there that's exposed to cosmic rays. Those cosmic rays destroy the crystalline lattice very efficiently. So we measure lines of sight and crystalline silicates in the interstellar medium. What we're forming our solar system out are about 0.02 to 0.05, 2 to 5%. Remember whenever I said that we saw crystalline silicates in comets, like Hale-Bopp, where we see these strong crystalline silicate features. And for Hale-Bopp, we see numbers up to 40 to maybe even 75% crystalline silicates. But comets formed cold. Where they formed, the temperatures were not sufficient to condense out crystalline silicates, to make crystalline silicates. And we didn't inherit them from the ISM. So how did we get crystalline silicates out into the comet forming region? Remember that to form them, you need very high temperatures. So you're forming them in the very inner regions of the solar nebula. To get them out and incorporated into comets, so we can actually measure them in the spectrum of Hale-Bopp, that indicates that there is a high degree of radial mixing of material in the grain formation era of our solar system. And we're taking materials that are being formed, these crystalline silicates, from the inner part of the solar system and mixing them out to where comets form, onto these cold regions. And if you're mixing stuff out, you're going to be mixing stuff in. There are a variety of radial mixing ideas out there, hypotheses out there, things from X-wings to turbulent mixing, to turbulent eddy mixing. There are a number of different models that are trying to get inner material to the out, where comets form. We don't know which model is right or which ones are all at play, because there's probably many of them working out. But in order to actually suss that out and to figure out what our radial mixing methods are and how efficient it was, how many crystals were being mixed out, it doesn't tell us how many materials are being mixed in as well. Very crucial if you want to understand how the Earth ended up being the Earth, how the asteroids end up being the asteroids. Well, and we need a measure of this radial mixing. And for me, the overarching goal that I have is to provide a constraint on these radial mixing models. I want to measure a good crystalline fraction, how many of these crystalline silicates there are in Hale-Bopp and other comets, so we can constrain how many crystals we need to mix out and how in a certain amount of time. So that's what I'm after. I'm after F-crist, the number of crystalline silicates in comets. I also would really like, rather than just a litmus test of this is how many crystalline silicates there are, can I retrieve any extra information as I'm getting how many crystals there are there? Can I pull out anything about how those crystals actually formed? So does the formation of the crystal imprint anything that I can detect in the spectrum? So can I actually get additional information? And yes, we can. We can get at some crystal properties that will give us additional information more than just how many crystals are there. And the three properties that I'm going to be focusing on that are in the 8 to 40 micron region are crystal grain shape. That's going to be the majority of this talk. And crystal grain shape, it can affect how strong each one of those crystalline features is. So each one of those resonance features, each one of those, say 11 micron feature, 10 micron feature, 23 micron feature. So it can affect how strong it is. It can affect how the shape of the feature. Does it just go up and come down, or is it a little lopsided? Does it look like a shark's tooth? So it's going to affect the feature shape and strength, and even the wavelength location. So the problem with the fact that it can affect the wavelength location is this ends up also being degenerate with composition, magnesium versus iron. So it becomes a pretty complicated problem. But we have to understand both the compositional part and the shape part if we're ever going to tease those two apart.
In general, do we have enough telescopes that can do spectroscopy in that range?
We currently have 0.
So how are you going to do this?
So we have a lot of archival data from Spitzer, and we have the isospectrum, and we will have James Webb Space Telescope soon. We can get a little bit of the 10 micron region equipped like on Gemini, but that's just the 10 micron feature, and we really want all the way out. We need those longer wavelength features to really start teasing some stuff out, and hopefully I'll convince you of that.
Okay.
So right now we're on hold.
I remember you saying like, oh yeah, all the telescopes, we don't have any more that can do spectroscopy, but you have enough data collected over the past 40 years to do this with? I don't know how.
Yeah, roughly 30-ish. You have questions up?
Did you say 98 was the last time it was here?
That was the only time I was here.
Okay, and so.
It won't be back around for like another 100,000 years.
Oh, okay.
Yeah.
So he was asking the data. you have-
2,500? Oh, because it was modified.
So all the data you have is from that time period? Is that what he was at, what Charles was asking?
Yes.
Okay.
Well, he has more than one comment.
Yeah, we have more than one comet, and we have a large archive, and some people actually still observe just the 10 micron region. So we can pull out a little bit of stuff. And then there are things like the Trojan asteroids, which show crystalline silicate features. The Trojan asteroids they lead and trail Jupiter. And then you have the P and the D type asteroids, which show crystalline silicate features, sometimes in emission, which is a little bit weird for asteroids. So there's a lot of other things that we can look at as well. So back to what grain properties that we're after, we also have the size of the grain will change the spectral features. And this kind of makes sense because as you get the size of the grain approaching the wavelength of light, you're going to leave the Rayleigh limit, and all of a sudden you're going to get some interesting effects going on spectrally. So the size of the grain can affect feature shape, strength, and wavelength location of the peaks, but to a little bit of a lesser degree than the shape. I have a nice paper that explores all the grain size stuff. I'm going to put that aside and not cover grain size, other than the fact that I use it in this talk. And then we have the chemical composition, the magnesium versus iron, which I already said, affect shape, strength, and wavelength location, and can be degenerate with our shape effects. So we got a lot of work to do. And previous to the work that I'm presenting, we would try to go fit, say, the spectrum of Hale-Bopp. So here it is again. And this is from Harker et al. 2002, where you add up the various components, you create a synthetic SED, and then you constrain that SED so it matches the spectral features. And then you take that as your answer. And then you can figure out that, say, you have about 50% crystalline silicates in the spectrum of Hale-Bopp. And this used 5 different components: amorphous olivine, amorphous pyroxene, amorphous carbon, and then forstrite and enstatite. But the problem with all the previous ones is these types of models that they're using, continuous distributions of ellipsoids, distributions of hollow spheres, things like that, they don't preserve grain shape. They statistically take care of grain shape, but they don't actually preserve the grain shape. They also don't account for the full anisotropic optical properties of a crystal like forstrite or enstatite, which has 3 different indices of refraction. So they can't preserve grain shape, which is something that I want, because turns out that how grains condense, the temperature and pressure environment will give you specific shapes. But also they can't fully treat all three different indices of refraction. So we need a new model. And now just a little bit more about this weird anisotropy of crystalline silicates. They are technically, so forsterite and ancetite are what we call biaxially birefringent. So if you're unfamiliar with birefringence, here's some calcite, and you can see it splitting as two different indices of refraction. So as the light comes through, it takes different paths and it splits the image. Whenever you go to something like forsterite, you have three different indices of refraction. Two are very close to one another, and one's quite different. So they're biaxially birefringent. So you have three perpendicular crystallographic axes, alpha, beta, gamma, which we just call ABC because we're lazy. And each has its own index of refraction. And this is very magnesium rich olivine. So this would be forsterite. And I just want to go ahead and give you a plot. So here's the wavelength, here's the N and the K, and the three different indices of refraction. And you can see that they're different from one another. Previous models have to do each one of these separately, and then they just average them together. I want to treat all three simultaneously. I want to make a model that can deal with all three indices of refraction at the same time. And whenever I do that, I also want to be able to build shape and put in composition. Which leads me to, what can I use? And what I use is the discrete dipole approximation. There are no exact solutions, or the exact solution of Maxwell's equations are only for spheres, spheroids, and infinite cylinders. You can't really solve Maxwell's equations for a shape like this or any realistic crystalline shape. So we need a suitable approximation. And we need one that can compute absorption and scattering efficiency. So how well does it absorb? How well does it scatter as a function of wavelength? And we have to preserve grain shape, grain size, and composition. And the discrete dipole approximation gives us the chance to do all of those things. So what it does is each one of these little green spheres here represents a single dipole, a polarizable element. And then I can go ahead and put those into an arrangement to create a shape. So here I've made a shoebox, a rectangular prism, a brick. So I can preserve shape. I can make a tetrahedron. I can make a whole variety of shapes. And then each dipole gets associated with a dielectric function. So it can carry the composition, your N and K, your indices of refraction. And then you have a user-defined effective radius, which is, if this was a sphere, what would of equivalent volume, what would its radius be? So now I have a model or an approximation, the discrete dipole approximation, that gives me shape, composition, and size. And then the way that works is you introduce an EM wave, a wavelength of light. Each dipole will respond, change the electric field, which will then all the other dipoles will change according to that, which will affect all other dipoles. So you have to do an iterative solution to stabilize, and you get an answer out. And you do this over a variety of angles. I usually use 64 different angles, and all those 64 angles of incidence are averaged together. The specific DDA code that I use is called DD-SCAT. I was using version 7.1. I'm now using version 7.3, but the work I'm showing today was on version 7.1. It's publicly available for Fortran, implementation of the DDA. There's a whole lot of things to increase numerical efficiency. So I use a complex conjugate gradient and fast Fourier transforms to make it speedier, but speedier is relative. So just as an example, this is quite computationally intensive. I was using NASA's Advanced Supercomputing Facility, Pleiades, and for a grain that has about 7,000 dipoles, with an effective radius of 0.1 microns, it gets longer the larger the grain size you go to. I'm calculating for 741 wavelengths between 5 and 41 microns. That takes about 2.5 hours using 64 processors. And to actually do my model, I need to do it for 0.1 micron size grains, 0.2, 0.3, all the way out to about 5 microns in size. It takes a while. And if I'm in a test shape, I need more than one. So I spent a lot of time running DD-SCAT models. But the inputs are a target file, that's the shape, optical constants, that gives you the composition, and then you user define the size, and you say what wavelengths to run over, and the number of orientations. And the outputs that you get, oh, we cut off a lot of them, but there's only one that I care about, the absorption efficiency as a function of wavelength. One thing that you have to do is you have to take your, I'm creating geometric axes whenever I make these shapes. So I have an XYZ axis, and then I have to assign the crystallographic axes. And you have a number of choices that you could do, where I could say X will be A or X can be C. So you can arrange them in different ways. So I will physically say each XYZ physical axis will get mapped to a crystallographic axis. So then you can even play around with weird asymmetries that you get by switching these things around. So hopefully I've convinced you that the DDA can handle shape, size, and composition. If you want any more details, I've got some supplemental slides. But the next thing we have to do is once we get that absorption efficiency as a function of wavelength, then we actually have to use that information to build a synthetic spectrum and then match that to Hale-Bopp. So I'm going to follow the tradition, and I'm going to use the five most abundant dust species we see in comets: amorphous carbon, amorphous olivine, and amorphous peroxide. You can approximate those with meat theory, so that's pretty fast and easy. Instantite ends up not being a whole lot of it that we see in comets, so I have not yet run the DD scat models for instantite. I'm just using some laboratory optical constants, or actually mass absorption coefficients. And then for Force-Right are my DDA models. And I'll just go ahead and walk through this. I have a step-by-step. So here is how I actually build a synthetic spectrum. And I'm going to walk through this as much as I can. So here is the flux that will be produced for a species X, and I'll be computing the emission. Absorption efficiency equals the emission efficiency by Kirchhoff's laws. So what do I have to put into this thing? So we have, let's see if those are supposed to pop up one at a time. I must have destroyed that right before I came up here. So here we have the total number of mineral grains that are in the species. So you need the abundances. Then you have how far away is the object from Earth. So the geocentric distance. You need the grain size distribution. So you need the number of each size of each grain going into this. And we use the Henner grain size distribution. Again, I have that in my supplemental slides. You need some black body temperatures, so thermal equilibrium temperatures for the dust grains. And of course, you need the emission efficiencies. And you need the grain size right there as well. So you can calculate the flux for each one of the different species that are going into this. And then you can sum them all up to build a synthetic spectrum. What does that actually look like? It looks like this. So here I have amorphous carbon, just looks like sort of a black body. And I have my olivine, amorphous olivine and peroxide. There's two broad amorphous features. Here's my forsterite. Here's my instantite. Add all those together and I get a synthetic spectrum. You might be thinking that looks kind of like Hale-Bopp. But we still need to constrain the model. So how do I go about constraining the model so I can say, oh, I have a good fit to Hale-Bopp. Now you can see that same synthetic spectrum. It was fit to Hale-Bopp. And you can see it plotted against Hale-Bopp. So I create an M by 15 grid where M is just going to be 5 to 8 different components. I started with 5 and I've expanded the model out to 8. And the 15 is just going to have 15 different abundance values. So I'm just casting a wide net. And what I'm going to do is for those 15 different abundance values for each one of the different components, I'm going to generate synthetic SEDs. And then I'm going to calculate a reduced chi-squared for each one of them. Pretty fast calculation. And then what I'm going to do is I'm going to find the minimum of that grid. And my a priori information is based on what other people have found. So I'll find the minimum of that grid, and then I'll recenter at that minimum, and I'll restructure my grid so it's looking at a narrower rim. So it's refining the mesh, honing in. And I'll keep refining, setting the new bounds be plus or minus 1 sigma. And I'll keep doing that until I basically get a stable solution where it's not changing from iteration to iteration. So I have a established grid size. And since I've been setting the boundaries to 1 sigma error bars, that also gives me the correlated errors between all the different components as well. And eventually I'll end up with a chi-squared constraint that has fit the spectrum, hopefully well. And this gives me a total number of parameters. So I have the different species, either 5 to 8. And then I have the 2 grain size distribution parameters as well, which I haven't mentioned yet. All right, so hopefully you now realize that I can go ahead and build synthetic spectrum, but I haven't yet shown you the shape yet. And this was actually started in my dissertation as a kind of a naive graduate student, where I threw the kitchen sink at it. So I created a bunch of, there we go, there's my timer. Oh, that's a 5-minute warning. So I created a whole bunch of different shapes. And what I was going for whenever I created these shapes is I wanted some things that were just sort of shoebox shaped. I wanted some things that had dipyramids on them. And I would use things like tetrahedron, and maybe I'll put 2 together to make a triangular dipyramid, do a tetrahedron, use something, see a whole variety of different shapes, the kitchen sink. And then I'd run them through DD-Scat. These are all for the smallest grain size, the ones that run the fastest. And what I want to convince you with this is that each one of these, so here we have our normalized absorption efficiencies versus wavelength. This panel over here is 8 to 13 microns. This panel is 13 to 40 microns. The top is a laboratory measurement by Tom and I et al. 2006. And then here are all my single grain size DD-Scat models. The absorption efficiency spectrum depend on shape. We've known this from laboratory, but now you can see that shape clearly has an effect. And now I have a whole variety of semi-realistic shapes that I can throw into my synthetic spectrum model and see how well they match Hale-Bopp. I have preserved grain shape. And I've treated all 3 of the different indices or fractions simultaneously using my DDA model. So what kind of result do I get? So my best fit is using the grain shape of tetrahedra. So this is the tetrahedron model, and that's tetrahedron for forsterite, this lab enstatite, and then me scattering for the amorphous parts. And I have a reduced chi-square. It's not the best number you've ever seen, but that's because there's all sorts of things that aren't fitting super well. There's this region right here that nobody knows what's going on that adds a whole lot to the chi-squared value. For our field, this is actually a pretty darn good fit. And it's the best out of all the shapes that I threw at it. And then I can calculate the crystalline fraction, and I get about 55%. So 0.56. I can even get the enstatite to forsterite. And we can see that there's little to no enstatite required. This is also consistent with the previous models that use like CDE or ME or distribution of hollow spheres. And we can actually use differences to figure out which ones are the best fits. So tetrahedron is significantly better fit than, say, triangular dipyramids. And now I have a model where, oh, yay, tetrahedron fit. But I don't yet know, are tetrahedron, is that important? Is that interesting? I don't know. I threw the kitchen sink at this one. I was just trying to make realistic grains to get a better constraint on the crystalline fraction. I hadn't yet gotten clever. So I wanted to come up with a way where I can not do exact crystalline shapes, but I can sort of cover the range of all possible crystalline shapes. And this is what I was doing back in 2013, where I came up with what I call shape classes. So I start with a DD-Scat model where I start with a cube. I constrain it so all the effective radius will be 0.1 microns. And what can I do with that cube? Well, I can stretch it out into a column, or I can squish it down into something flat like a tabletop, a platelet. So I do various extensions. So here's the cube, and then I'll extend, so one axis, either the A, B, or C to 1 point, where A is 1.2 times, B and C 1.4, all the way to 4 times. So a moderately elongated to clearly a column, almost a whisker, as we'd call it. I can do that for each of the axes, and then I can play the game again by platelets. So I can squish them down. And I can go all the way, I start at 0.8 for the axis that I'm altering, all the way down to 1/10 of the other axis. So a really, really, really thin platelet. And yes, you could add pyramids, you could make them irregular and things like that. But other than that, this kind of covers the generic shapes that you can have. They can be elongated, they can not be elongated, or they can be squished. And you can see here that as you elongate, say the A axis, you're taking this 11 micron feature and you're moving it to longer wavelengths. Same for the B, but for the C, it moves at the shorter wavelengths. And then you can see how it's affecting the other features in this 8 to 13 micron range. And you can see I've just traced all those. My point isn't to talk to you about how shape constrains this. You guys are not crystalline silicate people. But I will show you what it looks like for the 13 to 40 micron range. So you can see that all of these different spectral features are changing. So now I've done this shape experiment, and it allows me to create what I call shape classes. So I'll take everything that's about 1.4 to about 0.6, either squished or elongated, lump those all together because sure, they're elongated and squished, but not that much. Most of the different axes are about equal. And I create what's called a quant, which is average all of these together that are between 0.6 and 1.6 to create a quant. Then the really squished ones, I call those the platelets. The really elongated ones, I call those the columns. And I have them for the elongated along the A, B, and C axes and squished along the A, B, and C axes. So I end up with what I call shape classes. And this shows you the big variety that shape can cause on the spectral features for forsterite. You see there is a big range going on. And what's really interesting is I'll show you that it kind of plays out because you actually can fit certain shapes to the spectrum, but these end up giving you some distinguishable spectral features. So now I can go back, instead of throwing the kitchen sink at it, I can expand my model. I can chuck out enstatite since it wasn't a huge component, and I can put in a new grain shape for forsterite. So now I can have, say, my tetrahedron, but then I'm going to mix in C platelets as bricklet. And I can repeat my spectral model fitting, and you end up with a better chi-squared. And it shakes out, we have 92% of the forsterite grains are tetrahedral in shape, 8% are these sort of C platelets. If I have time, I'm gonna come back and comment on them. And then after that, we pushed it. We expanded out to 8 components, no, not just 5, but 8. We didn't use enstatite, so we could use a whole variety of different shapes. We could throw the shape classes at fitting the spectrum of Hale-Bopp. We could really see what shapes work for the crystals and which ones don't. And that's what this is showing you down here. As you can see, my synthetic spectral fitting got more complicated, but the chi-squared came down to about 5.5. We're doing a better job. Oh. The question is, what shapes does the fitting routine favor, and then which ones does it fit out? We didn't really tell it which ones to do, but it would always end up favoring B columns, B platelets, and a quant grains. And every time that we include A or C columns, the chi-squared minimization routine would kick them out. There'd be a 0 contribution from it. So the Hale-Bopp spectrum favors these ones and removes these ones. JT, do you mind if I get back to your question after I finish up? Thank you. I can see the chat.
Yeah.
So now the question is, are those shapes, do they have any physical meaning? Have I actually done anything by preserving grain shape? Now I want to go back to this Comet et al. 2008 experiment where they used some vapor chambers, they heated them up, they made solar nebula-like pressure conditions, and they condensed out forsterite grains. So you can see they're quite small forsterite grains. There's a scale bar of 2 microns. And they noticed that for different temperature ranges, you would preferentially form different shapes of grains. So from the 1000 to 1400 degrees Celsius, sorry for the switch from Celsius to Kelvin, they use Celsius, so I put Celsius up here. I'll switch back to Kelvin here in a minute. But you end up with sort of a quant type grains. And here's actually that grain I was showing you before versus one of my DD scat models. Then for 700 to 1000, you'd end up with these platelet type shapes. And then for low temperatures, you'd end up with columns. And the ones that form are A and C columns. Interesting. So let's compare that to what was improving my fits and what was not improving my fits whenever I modeled Hale-Bopp. Well, here a quant improved my fit. B platelets improved my fit. A and C columns were removed from my fits. So the conclusion that I'm drawing for this is that it's likely that the crystalline silicates in Hale-Bopp are best represented by high temperature condensates, which means that they formed very, very, very close to the sun in the solar nebula, where the temperatures were sufficient to form these kind of grains. So now we're actually having some information about the potential formation regions of the silicates that end up in Hale-Bopp. And we have HEP+Astro for a measurement of that, so we have a constraint on how much radial mixing is going on. So how much time do I have left? What time is it?
It's 4:20.
Huh?
It's 4:20.
4:20?
Mhm.
What time is this then?
4:35-ish.
So I'm gonna skip because I want to answer some questions. But if any of your questions are about, hey, you had that model where you had tetrahedra and you had the C platelets that were sticking around, that actually might have some intriguing physical meaning as well. But it's strange that the shape classes did not include C platelets. That might be a case of overfitting by choosing all the grain shapes that fit best is going to favor that 92% and not the 8%. But if you want to know about this, I do have this is some of the work that I'm currently doing, where I'm working with a team that's used a high velocity gun at Johnson Space Flight Center, and they're shocking force right grains, which induces these planar dislocations. And now I'm trying to actually model these planar dislocations using DD-SCAT. So here's pre-shot, so pre-impacted. So these are unshocked, and then you get some structural changes after they're shocked. And I've been trying to build more advanced DD-SCAT models of more realistic grains, where I've actually put some bands of amorphous material to try to mimic these C planar dislocations to see how well I can reproduce their experimental results. That's a paper that we hope to get submitted by October-ish. And I do want to go through the quick little summary before I answer some questions. So the effective grain shape is important. Hopefully I showed you that with my whole variety of kitchen sink models and my shape classes. And they have structurally distinct features, which whenever we actually apply that Hale-Bopp, we might actually be able to pull out some information. And the information that I was really interested in is where were they forming? So what were the sort of environments where you condense grains for the shapes that fit? And of course, I was interested in the HEP+Astro, and pretty much every one of the best fit models that changes a little bit, but they come out between about 55 and 56% HEP+Astro. So it's a pretty stable number that I'm getting with my modeling. Whenever I include enstatite as well, I get a very low amount of enstatite. And I can even get the carbon and silicate ratio as well. And then I have the ones that favor, the grain shapes that favor are these high temperature condensates. And I do have this interesting thing that I might be able to tell some of the collisional processing, detecting some of the shock grains that would exist in comets. All right, I'll stop there.
All right, thank you very much. So who has questions? Let's start with the students.
I do have a question. So for the spectrum of Hale-Bopp that you were showing, and there was that region that was very noisy from.
Only one region that's very noisy?
And you said no one knows what's going on
Yeah.
there.
Isn't that the,
Come on. This one?
yeah, isn't that where you're joining the spectra from two different satellites?
So you do have some high fogs data here, which is putting some of the noise, but it always ends up looking a little bit strange here. So some people are proposing there might be an organic component that's down here as a feature that's there. But yeah, the noise that you're seeing right here is mostly from high fogs. If you're looking at a Spitzer spectrum instead of an ISO spectrum, this is also where they have this thing they call the teardrop feature, which they haven't been able to figure out whenever they're splicing the different orders, because whenever you create a spectrum, you break out the light into one order, and then you have another order by a cross disperser. Then you have to take those spectra and stitch them together.
Right.
And for some reason, at 14 microns with all Spitzer mid-infrared spectra has this weird disjuncture, this weird feature they call the teardrop feature. So nobody really trusts what's going on in this region, but this is ISO right here. So maybe it's a little bit better, but we do have some features there that don't match just my silicate model, and it could be from something like organics. Some people have done Comet modeling where they've thrown their own kitchen sink of compositions out there, most of which don't make sense. We don't expect them to be in comets, like certain hydrated silicates and other things as well. and they still can't even match that feature.
So is it possible it could be just a computer error rather than?
It could be a problem with the data. I like to keep a little bit of optimism and think that there's some discovery there that we haven't made yet. The problem is we don't have a whole lot of optical constants of things. So building these models is very optical constant dependent. There's not a lot of people out there getting us optical constants. Most of the ones that I was using here for Foresight, I was using ones that were taken in 1974 by Stayer et al. I've done some of these models using the YANA database as well, where they get optical constants via laboratory measurements. But yeah, we're very limited on optical constants. If anybody ever wants to change career paths, become a lab scientist that gets optical constants, please give me your business card.
Atomic physics in general, not just the optical constants, the whole field disappeared,
Hmm.
and we need it, astronomy needs it.
James had a question in the chat. So James, you want to just ask it out loud?
Yeah. So did you use the machine learning, or did you use machine learning to accomplish the best shape class fit, or did you do that all manually?
No, it was used that sort of refined mesh grid with chi-squared minimization.
All right, other questions?
Yeah, I had a follow-up to that because, so I was thinking about what benefit you might gain from doing something like he's proposing. The problem is you still have to do the simulations to train the machine learning model. Essentially, it seems to me like what he's saying, and I could be wrong, I don't want to put words in his mouth, but what he's saying is you replace the optimizing against the chi-squared for just coming up with some loss function where it's the difference between the spectrum measured and the calculated spectrum from your scattering model. And then you scan through the parameter space of all the simulations you have, and then redo it and see if it comes up with a different, if it optimizes against the different, whatever for, the difference for the different shapes.
So you can see one of the things I was looking at, I wasn't going for machine learning at all with this one, but I was just trying to understand where my models were not matching, because there's some interesting information, some physics that we're missing there. So what I'd do is I'd add up all the amorphous stuff, and then I would take the spectrum, subtract off the amorphous, leaving what I call the crystalline residual. That's what you can see in yellow right here. So you can see that my model does not match this feature very well. And every model that I've put, and every model that I've seen misses how broad this feature is for Hale-Bopp.
Well, I guess
That's not a machine learning.
yeah, I guess my question pertaining to that would be, would you see any benefit? Because on the one hand, you still have to train any machine learning, so you're still gonna have to do all these computationally expensive simulations. On the other hand, it might be better able to scan through the parameter space of all the different shapes that you have, assuming you have it, with higher granularity and more fidelity than just looking at the chi-squared, for example,
Yeah.
is a possibility. Do you see any benefit to that?
Possibly. I think anything that could complement any of the modeling methods that we have out there that can give us some insight, especially since we have so many parameters that are running around with this. This is why it's so hard to get funding for anything in the mid-infrared, because everybody has strong opinions on it. And it always comes down to you didn't fully explore the parameter space, so you can't actually get an answer.
Yeah.
So anything that can help basically convince people, and I mean, machine learning is kind of exciting for people. So maybe
The other thing that
you might be able to find some, if you could actually get a spectrum, you might be able to find ones that actually do start filling out these weird parts that don't match.
The other thing you could possibly explore, and I think there's some discussion in the chat, is if you could possibly replace. So you have these scattering simulations, which are computationally expensive. I think you explained like how long it took on NASA's cluster. But if you could look at multi-fidelity modeling, where there are parts of that model phase space that you can replace with less computationally expensive model, parts where you need the high fidelity, so you do the full simulation, and then see if that can reduce any kind of I don't know if that's a
So
bottleneck.
I'm doing that by using mean theory for the amorphous components and laboratory stuff for the small component density type.
Okay.
The reason that we're using DDA model or DDA method and using DD stat is because it does preserve grain shape. So I haven't found any method out there that cheats that. and gets around that. And we've done, so the person I did most of this research with, Diane Wooden, has expanded this research where she's actually putting these crystalline grain shapes in larger aggregates. And that shape effect bleeds right through as well. So I can't see any modeling method that would get around that could speed that up. What you need is just somebody that will be a grad student whenever I ran all these models that has nothing to do for years other than to run models.
Yeah.
And then build the library of it so you can do models.
Okay, and then last question, I think what was in the chat was just, I don't know if it was another question or just further discussion, but I did have one last question not related to the machine learning or modeling. Can you help me understand, so you mentioned with these amorphous silicates, there's two effects that sort of distort the crystal grains. Cosmic rays and then just, mechanical collision or fracture. In the case of the cosmic rays, what I'm kind of envisioning is you have this crystal lattice and then a cosmic ray comes in, disrupts the bond between two lattice sites, and then a bond reforms elsewhere. And then this happens over and over again. Wouldn't this, if this is true, and I could be wrong in how I'm thinking about it, wouldn't this just be random and you would, just end up with no, structure after long enough time being bombarded?
No long range structure. Yeah, so basically, that's what we're saying. That effect right there is what we're calling amorphous,
Okay,
instead of like a true amorphous thing, which would be a glass.
yeah, okay,
So you
so,
don't have a crystalline structure. You basically just destroy the crystalline structure in a random way sufficiently where we call it amorphous.
okay. Do you have an analogous thing with the mechanical stress or collisions as well? Or no, an analogous effect or the similar
So
effect?
it might not work as well with mechanical stress type things because you preferentially will break a crystal. You'll break the crystalline lattice in certain ways with planar dislocations. And based on how foresight actually behaves, its cleavage, you're going to break it along the c-axis. So this would be the c-axis. So these are perpendicular to the c-axis.
Mhm.
So maybe not as much with mechanical, but the cosmic rays, yeah, sitting out in outer space for that long is going to get them. And we actually measure that. Yes. Oh, and before I do one more question, could somebody tell me what time it is? I lecture at 4:45.
4:32.
4:32.
Okay.
You're so good.
I may be thinking about this too simply, but you've taken these models and everything. Can't you like send this off to the experimental people and have them like build these silicates that you've modeled and with the same ratios, and then they just add more stuff to it to try to fit the spectrum? Like, could they do it experimentally and just throw stuff at it and see what makes it look the same?
So
Or is that just too?
here's our best experimental shape or laboratory experiment shape model. This is Comet et al. 2010. You can't really control what kind of crystal shapes you're going to get.
Okay.
And Comet et al. I don't think they made enough so we could actually do any measurements. Definitely, I don't know how to get access to those. But this Japanese group, Comet et al., and there's another Japanese group, Tomanai et al., they do some pretty amazing work. And what they've done here, they've created a variety of different grain shapes. So typically what they're doing, the grain shape is a function of it's been mortar and pestled, either by hand or through a machine. And then they'll basically grind it up and then they'll recrystallize it by annealing. So they'll warm it up and rebuild crystalline structure that way. So they end up with a variety of different shapes. So you can see that there's a change there.
Okay.
But whenever you're creating these in the lab, do they have any astrophysical sets? Like
Right.
grinding them by a mortar and pestle, is that what you expect for the shape of grains in, say, Hale-Bopp?
Right. Okay.
So I wish, again, there's just not a lot of people working on these.
Could we irradiate them in a lab?
Yeah.
Irradiate them to control the shape?
No, not the show. Okay.
To simulate the cosmic rays.
Oh,
Or the dissection.
I mean, you could irradiate these and amorphize them that way if you want to.
That part's easy. The hard part
Yeah,
is
the hard part is the
recreating the
shape.
conditions in a cloud that form the grains.
Okay.
Okay.
Yeah.
It's by terrestrial standards, it's a very good vacuum. If you have AU of it, it's actually a mechanism for forming stuff.
And if you want to know what some of these grain shapes look like, this is the condensation experiment. This is an atomic force microscope image of a IDP. So you can see it's kind of jagged and it's got these facets, nice clean edges.
Are there any planned missions to get actual samples from comets?
So we collected stardust grains. So a lot of this stuff, and I haven't gone through and fully correlate all that. Diane Wooden has done a lot more work on that one, but we get very, very similar sort of F-crysts, and we see sort of similar grain shapes as the stardust grains. So that's the only sample we've returned so far.
When you say Stardust.
Oh, so Stardust was an ESA mission where they had a spacecraft and it flew through the tail of a comet,
Okay,
and it captured dust grains in aerogel and then returned that aerogel to Earth.
okay.
I think you might know, you might remember this. I think that might be the one where the parachute didn't deploy, so the
Yeah.
sample capsule went on the ground.
Oh,
It took them years to get any.
Yeah.
data out of it.
So, and you're just pulling out one grain at a time. Also, the aerogel, they used aerogel, the least dense material on there, because it wouldn't alter the grains. No, they were still thermally altered and mechanically altered, but even by slowing them down with aerogel. Which is why a lot of the times we like IDPs, because these are basically the dust grains that fall into the upper atmosphere. So people will fly planes. There's a nice gel. I don't know what kind of gel they use to collect it or not. This is George Flynn, people like that to do this. And they'll collect the IDPs as they sort of gently fall into the atmosphere. And then we'll sample those.
Neat. Okay, I had some more questions, but I think you have to teach, so maybe we should.
Let's do one more.
Okay,
My students can wait.
I'm a little curious, like, how do you, it's obvious that you haven't like completely over constrained this because you still aren't able to match some of the portions of it, but I do wonder if there are like parts of it that you have over constrained, like if there's.
That's what I worry about with the
Yeah.
8-component model.
Yeah, so
is-
how do you check that, I guess? How do you look into that?
I don't know, you got any clever ideas?
Okay, so it's hard to tell. That's
Keep running models and look at things like stardust grains, try to anchor it into some sort of reality. But yeah, there's so many different things you can play around with. So you have, let's see if I have the grain size ones. Details. So this is how the spectral features change with grain size. So you can see I'm choosing the effective radius here and all sorts of different changes in the spectral features. So now you have size, it's something you have to worry about. And what's the grain size distribution? What is it shaped like? Where is the turnover point? Where is the peak? Is that the same for all comets? Is it not the same for all comets? What is this, the tail end slope as you go to larger grains? So you got that problem as well. And then you have, oh, well, how much iron versus how much magnesium do you have? So here you have wavelength. And these are these different spectral peaks. And the red line are just linear fits to how it changes as you go from complete 100% magnesium to 100% iron. And what I've overplotted here, so these ones are lab experiments in the range that shape causes. And then my boxes right here are my kitchen sink range of peaks based on shape. So what I was going for here, I was trying to identify what peaks here would be sensitive to grain shape, but not to composition, and which ones would, if not sensitive to, or not sensitive to shape, but very sensitive to composition. So you could tease out things like that.
So if you had a larger spectrum, would it be helpful to being able to, I mean, other.
Yes, so there are features, there's a 65 micron feature.
Yeah.
That I think is insensitive to a lot of different things. But very sensitive to composition, so similar to this feature right here.
Cool.
So there are more features out there. Come on, James Webb, please launch. We can't do any more delays. Keep all your screws, don't lose them.
You said soon. Do you know what the
December 18th.
it's December, right?
Okay.
Or is it the 17th? 17th or 18th is the planned launch.
Should do watch party.
I
think we're off.
do not want to jinx
We're
anything.
Not-
Okay,
yeah.
don't look at it.
Anyway.
Yeah, don't even mention it.
Yeah.
That'll be
It's like
enough to
Voldemort,
cancel.
you can't
If I
say it.
say its name 3 times in the mirror.
Yeah, one of the screws will fall out.
Without a space shuttle, if they launch James Webb and there's some kind of problem with it,
Yeah.
will they be able to repair it?
Not a chance.
You know, they had that problem with Hubble where they had to.
They will, JWST won't, it's launch and gone. It either works or it doesn't. It's too far away.
Yeah, it's.
I see that there's still
So-
plenty more questions, but I
I'll
think we
see
do
if
have
I
more
can
really
answer
good
the question.
questions.
I have a quick question, Sean. Did you say that 1200 degrees Kelvin was what about the temperature was when this comet was formed? Is that what I heard? you
Where
say?
the crystalline silicates were forming, we
Yeah,
would have
due to the
temperatures
shape.
in that range if
Okay.
my shapes are right.
Does that tell you something about the radius away from the,
But it tells you where we're getting the condensation of the crystalline grains that ended up, at least in Hale-Bopp.
this?
So we need to do other comments as well to figure out if all comments are the same.
It was formed during the formation of,
Okay, we gotta cut it off.
Yeah,
Sean has to go.
I lecture in 5
Yeah.
minutes.
All right, but thank you so much.
Thank you.
Stuff on my office. I'll answer all those questions. Thank you, everybody. This is- Well, I guess I should log out of Zoom, shouldn't I?
All right, bye, everybody.
I hope I
Space is
gave
so
everybody
cool.
something a little bit different.